Good morning, everybody.
Yep.
So I'm Arno Kolster. This is my colleague Ryan Quick. We both actually won the IDC Innovation Awards. It's not myself.
And I do infrastructure, not databases. But other than that, you're good.
So we usually like to talk together because we've been, between the two of us, we've been at eBay, PayPal for over 27 or 28 years. So it's been a very interesting journey for us. And we'd really like to talk a little bit about, this is a long title, but we'd like to talk to you today about what we've been working on in the last couple of years. The fraud detection work that we did several years back lent itself to allowing us to move forward with a lot of the different technologies that we've learned about and start looking at operational analytics. Operational analytics is a new field for a lot of analytics areas because everybody looks at business analytics. They're more concerned about how do we understand how many customers came to us last quarter, or how many transactions have we done last quarter. We didn't want to touch on that. We wanted to touch on data that's not being looked at, that we have lots of. So in our case, we've got lots of web logs, we've got lots of application logs, we have machine data, we've got data center metrics, and we wanted to take all that data and understand exactly what we can do with that data and also start modeling with that data to make our operations seem much easier to use, as well as reduce costs in different areas, i.e. the data centers, as well as operational activities in monitoring and our operations groups. So we started looking at this. This is not happening. Okay, so we finally started looking at what can we do with all that data we have, and we looked at it from the perspective of an ecosystem. So an ecosystem, i.e. in this case, is an interaction of a bunch of different variables. This is a perfect ecosystem. Everything is in balance. You've got fish, you've got coral, you've got the temperature of the water, you've got perfect sunlight, you've got nutrients. It's a completely balanced ecosystem. What we wanted to understand was what happens when something goes wrong in that ecosystem? What happens if you notice a drop of oil start permeating the water here, and what does that do to that perfect ecosystem? So we're basically looking at predictive algorithms and how they match in this ecosystem and what kind of problem that happens. So we decided to take the same analogy, i.e. all the data that we're gathering from our machines, and start looking for predictive models and looking at what potential events are happening through those models that could show us a problem that exists. So this is our ecosystem. This is one of our data centers. I can't tell you where it is, but it's in the foothills of the Rockies. This is an eBay PayPal data center.
It's in Salt Lake.
It's in Salt Lake.
We can tell you. It's not like we can hide it, right?
Anyways, so this is our ecosystem, and we wanted to understand what's happening inside that system, i.e. what are the machines doing, how are they interacting with the airflow, the temperature in the data center, what are the applications actually doing on the servers, and how are the interactions happening between all those variables. And this is a big task because nobody's ever done this before. We were gathering all this data and just sort of looking at it and throwing it away. We decided, because of our fraud detection architecture with HPC, we decided to take all this data and start consuming it and understanding what this data center was doing. So what are we trying to accomplish here? Well, we wanted to gather, obviously, all the data we could and understand what the PayPal system was doing. We wanted to understand its capabilities. We wanted to understand its capacities. We also wanted to create a self-healing system where if we do notice a problem, it takes care of itself so that humans don't have to interact with that. Because when you get humans interacting, it takes a longer time for the fix to be done than a computer actually fixing it. We wanted to understand the capacity so that we can model for growth and performance. And we wanted to leverage everything we learned from the fraud detection real-time streaming and apply it into the model for the data center. We also wanted to reduce the costs of running the data center. So for instance, if you look at a typical PayPal day, it goes up and down as far as transactions are concerned. There's a peak in the US and then there's a peak in Europe. We wanted to understand how that actually is working so that we can start powering off and on machines as they go through the day, because that reduces costs. We're not looking at creating revenue, we're looking at saving costs. So that also adds to the bottom line. Our goal, which is a crazy idea, but we really want to be able to take a virtual data center and move it around the world so that we're reducing costs everywhere we go and allow us to purchase power where it's cheap through the night around the world. It's a big task that we're actually looking at it in reality. So what are we up against in real time for operational analytics? Well, we've got the 4 streams that I mentioned earlier, machine data, application log data, social media, as well as data center metrics. Those are the 4 streams that we're gathering today, and we're doing those at the rate of 3 million events a second. So from an enterprise perspective, that's huge. From an HPC perspective, it's real-time data that's being ingested, which most of the HPC environments we know about generate static data sets, they load them and work on them. These are events that are happening as they come in. We also do about 25 terabytes of data an hour that's being ingested, 20 megabytes of machine data.
Yep, per second.
Per second, and about 54,000 metadata interactions that we've already graphed out. We also have increased streaming, customer service, and social media events happening per day. So between all those different data sets, we're ingesting those, looking for patterns, looking for anomalies, and reacting to those. What are the axioms that we came up with? We call this systems intelligence. We want the system to become intelligent and understand itself so that we can understand it also. We wanted to keep things in memory as much as we can so that we have a rolling window of the events throughout the day. So we create a huge window of all the events and we pass them through the models. So for instance, we sometimes release push new releases on Thursday nights in the US, actually in San Jose. At the same time that happens, people in Germany are waking up, in Europe are waking up and they say, oh, I want to make a payment using PayPal. And then if they have a problem, they'll start calling our Irish customer service center and or start tweeting. So the problem is that if there is a bug, it hits the Germans first and they start calling. That used to take several hours to determine what caused that bug. With our systems intelligence, we're now able to correlate all those events together and say, this release is causing something to happen in Germany, which is causing an increase in customer service calls. So using all this information that we're gathering in real time, we're now able to increase customer satisfaction, decrease downtime, and also decrease costs. We wanted to be able to have a huge shared data set so that it can be acted upon by different processes. Not only is that data set being used by us, it's also being used by the fraud detection people. It's also being used downstream in other analytics. We also wanted to be able to use predictive models that we built from the fraud systems and apply those into the systems intelligence streams that we're building. So it's basically a blend of HPC and enterprise in terms of coming from an enterprise business perspective with architecture that's already in place, because we are a web company, web scale company, but we're applying the HPC architectures that we learned about several years ago with the fraud detection system that we put together. So we built purpose-built systems using underlying technology. We're using RDMA clustered file systems and to reduce copy times. Now these are all HPC kinds of things. We're using Lustre. We're using streaming analytics coming from an enterprise environment, complex event processing, event stream processing, and some patented technologies that we've put together for the digital signal processing work that we've done. And we also have downstream analytics environments, traditional EDWs, Hadoop, etc. All right, so I'm just going to quickly go through the flow to give you an overall view of how things look, and then Ryan's going to deep dive down on each of the pieces and tell you why we built things the way we did.
I do get to talk.
All right, so the flow that I mentioned earlier, there's 4 incoming streams: machine data, application logs, social media, and data center metrics. All that gets thrown on a message bus. Each box represents many different boxes, or many different servers. I just simplified it for you. Those message bus pushes events into several different application servers, and there's a little CEP box there for complex event processors. So all those events get pushed through the complex event processors, which are actually running models against the data that's coming in. We use a large shared memory system that I mentioned earlier for storing all the events so that the models can actually relate to an event that's happening now to an event that happened maybe 10 minutes ago and say, well, this CPU is showing high usage. If that same CPU shows high usage 10 minutes later, there's going to be a problem and react to it. We also have something that we call augmented stream analytics, which is traditional enterprise databases on the side that allows us to actually do a quick call to the database as the events are streaming through and either increase a counter or look for something on the side and push it back into the stream. And we have traditional offline analytics on the back end with visualization or machine learning with our data scientist who actually looks at the models and pushes the models back into the complex event processors. So we have an iterative process that actually allows us to be able to look at events, model them, push them back into the stream, and capture things. And then we push the reactive analysis and any changes that need to be made back to the monitoring and the remediation engines.
Okay, all right. We told you all that tech stuff so we can stop talking about technology and talk about why we think you ought to do some of this stuff. So I'll go through how those different components are blended from HPC world and from enterprise stuff. I'll point out where we picked an enterprise solution here, we picked an HPC thing there, put them together. But first I want to talk a little bit about why we think blending these two somewhat different systems together is actually a good idea. So first of all, I'm going to talk about this slide, which you probably can't read. But basically, this is data that originally started with Ray Kurzweil's book, Singularity is Near. We filled in, he sort of stopped his analysis at about 2008. We filled in some data since then. So what you see here is a logarithmic graph of computational power of different brains. So we have insect brain, mouse brain, one human brain, and all human brains going up to the top. And you'll see that we were on an exponential trajectory computationally up till about 2008 or so. That's sort of the bottom line going that way. But what happened in about 2008, if you start looking at computational power added on with accelerators and things like that, we actually now have a double exponential curve. So that's the second line. So we've actually increased even the rapidity with which we were gaining ground on bioengineered brains, so to speak. The trouble is with that, we're not quite sure the right way to manage things, right? So we're actually pretty confident, us not being hardware guys, we can sit back and watch what's going on in the hardware and say, you know, we don't know how they're going to figure it out, but it's unlikely that all of a sudden this is going to tank. If anything, the trends say that we'll get another exponential curve in another, decade or so that goes even steeper. What we worry about, though, is what is it that we're supposed to do in order to bring the game alongside the hardware, right? And what we've figured out is that we've got to comprehend, model, and design for the human capabilities in the system. So when we're putting something together, it's not about the hardware. It's not about the particular solution. It's not about a particular use case or even a group of use cases. Instead, what we have to do is figure out how to build new building blocks all together, right? And so that's kind of what we're going to talk about sort of for the rest of this is one, how you go about doing that. Is it a good idea? What does it look like to your business if you do? Those kinds of things. So back to the stuff that Arno was talking about. Here's the components in detail. Again, each one of these represents systems of servers. We just kind of put it in one square to make it easier to read. Here we adopted enterprise technology the whole way. The enterprise guys have messaging down, and acquiring data sets, they also have down. We can ingest data, although we don't actually ingest, we publish and subscribe to most everything. But we can take lots of small soldier computers, put them together, grab data or consume data from lots of different data sources and publish it back out. Messaging is also something that we took from the enterprise world. We mentioned on there that we're up against 3 million messages a second. We've benchmarked our messaging system at over 100 million messages per second, so we're not concerned in the least about being able to actually handle that much data on the wire. So again, it's another place where we said, you know what, the enterprise is a good place to go shopping here. But it starts to get more interesting in this space. So if you saw on that previous slide, it's pretty simple math to figure out that if you want to look at things right now, a function of right now is basically down to memory. The fastest component that we can get that can store something in the computer is true memory. So we have systems that on average keep about 7 minutes of real time on sort of a normal, say 96 gig of memory, physical system, right? It equates to about 7 minutes worth of stuff that it can look back in time for. And that works great for most things where you're just trying to count stuff or watch for occurrences. But it doesn't do so good if what you're trying to do is essentially pretty rare. And so let's say you detect an anomaly now that if it was correlated to something from yesterday might mean something interesting for 6 hours from now. That's difficult to do when you can only look back 7 minutes, right? So one of the things that we decided to do is take that middle node, that big one, that goes down to that shared memory event window, and we decided to take HPC hardware, shared memory system there, and apply that. That particular node can go back about 48 hours in its memory. It behaves just like the other guys, right? It sits there. I should point out we are actually using InfiniBand for transport here, so we get the benefits of RDMA across the entire system. But and that's true above. The message bus for us is implemented over InfiniBand. But at any rate, so that's one place where we made a specific choice to go with an HPC type architecture, even though we still slammed it into the middle of what looks like a normal to us enterprise cluster of multiple nodes. The OLTP database again is enterprise technology. We're very good at that, and OLTP still reigns supreme if you're doing small transactions, and it will for the foreseeable future, we think. However, you'll see that we augmented there with a graph database. That's a technology that's coming from the HPC world. It's still in a bit of flux, and it's still in flux on our side too, so we've changed that out a couple of times. We'll probably change it out again before we settle, but we do recognize the need for that type of structure there. So we went with it in that case. And the purpose of that augmented stream, this is what that section on the side is called, augmented stream analytics. And that's basically what we have on the wire is useful, but it doesn't necessarily tell us all of the story, right? So, cool, screensaver. So while they work that out, it doesn't necessarily tell you the whole story. So what we want to be able to do is if I need more information than what I got in a particular event packet, say I got, Arno and I are exchanging money and it's in Japanese yen and he's initiating his transaction side from Tokyo and I'm in Toronto, for example, we know we have 2 borders to cross plus a 3rd jurisdiction for where the transaction occurs inside the United States. We have at least 2 currencies to resolve. We may need to go get some ancillary information about rules, about currency exchange rates, and those kinds of things. We can pull that in from these side databases, as well as rules for relationships. Are Japanese allowed to exchange right now with Canadians and that kind of thing? That's the type of stuff that the graph will tell us. Anyway, we pull that stuff in, add that to the information that we have on the wire, and then go ahead about making a decision. At the bottom again, this is another mix. So you see Vertica there, which is an enterprise choice, although it's one that we've been arguing should be an HPC choice for a long time. We run that on top of, however, a InfiniBand-based scale-out cluster, which I think we're the only ones in the world that do that. We had to convince Vertica to let us do that, but it runs very well. Our machine learning and visualization is actually a mixed bag, ranging from the open source to the commercial. In those situations. And so it's also a mixed bag of HPC, although we have lately been using our shared memory systems for more and more machine learning work, especially on the for the commercial product side. We like the commercial offerings in the machine learning space. They do consistently outperform the open source stuff. However, our systems are far larger than anything they imagined running on, so we're actually assisting some of our vendors in looking at things like accelerators and shared memory and things like that on the machine learning side. Our data scientists are just as Homer as ever. We'll keep them that way. So this is sort of, we talked about having the sort of obligatory hardware slide in here in what isn't going to be 100% technical deck. But we're going to put it in here mostly so that we can illustrate where we actually are really combining technologies together here, but I'm going to let you talk to it.
So yeah, we have the hardware there because we do want to show you we actually are running HPC gear in our data center. And when I first started speaking about HPC and enterprise a few years ago, I was hearing all about these 100,000 core clusters and 200,000 core clusters, and I said to Ryan, I don't really want to talk about our 96 core cluster, but it's an interesting story. We're up to 3,600 cores now, which is pretty good for us. And
that's as of last night. I calculated it all again, so these are numbers as of yesterday.
It's a start. So here are the numbers. 24 terabytes of memory, 1.2 petabytes of storage, InfiniBand, FDR, QDR. Eventually we'll get to the EDR. We are starting to look at some parallel programming, which is brand new to the enterprise environment, but it's something that HPC has been doing for years. From the enterprise side of things, we're bringing messaging, the OLTP, OLAP databases that we talked about earlier. We're using traditional command and control monitoring, things like that, which from a perspective of real time and availability, PayPal definitely needs. HPC environments don't normally have that particular requirement. We do.
Telling folks it's a free-for-all out there doesn't go well with the Securities and Exchange Commission.
And of course, we also we have traditional Hadoop and machine learning environments on this cluster, and we also use Java and high-level programming languages, Python, Perl, etc. So what are the benefits that we derive from everything that we've been doing? Well, we understand now the visibility. We have a visibility into the health of our ecosystem, right? We can tell if a drop of oil lands on that ecosystem if it's going to cause a problem. We now are able to self-heal, and we have less reliance on humans. It's not a good thing that we have less reliance, but humans can't comprehend the system anymore. We've grown so large that not a single person can understand all the interactions between all the servers and all the code flows, everything. It's just too large. And I think a lot of enterprises here probably feel the same thing. We've had thousands of developers come through over the last 15 years, and they're building things and they're coding things. Just nobody understands the interactions anymore. So we're able to start doing that, looking at how one code flow interacts with another code flow and start optimizing those code flows. We also have the cost benefit to the business, as I mentioned earlier. It's cheaper to run our data centers now, which is a huge savings, especially when data centers cost millions and millions of dollars to run per year. So we have a huge benefit there in cost savings.
All right. So yes, it all works, but is it worth doing this type of thing? Is it worth the headache? And we're not going to kid you, it is a headache. That's what we're going to talk about for the rest of the time here, is whether the headache's actually worth it. Is it always a headache, or is it just kind of initially pain? So not hiding anything, challenges, right? Okay, these are we are going to go into detail on these, but we basically boiled it into some buckets, right? There's some technical expertise that if you're an HPC guy and you're going to try and bring in enterprise type stuff, if you're an enterprise guy, you're going to bring in HPC stuff, you will have a technical expertise gap somewhere. We'll go into what those look like, but you're going to have to own that and manage it first. Second of all, this is depending on which side you come from, your focus is likely going to shift. So for us anyway, reliability is absolutely foremost first. Performance is second, which means that we will and often do tell our HPC vendors we don't care about the extra performance. We'd rather have it fail over successfully, right? Which they're like, but we're like, it's okay, right? And then, of course, there's a lot of social aspects for running alternate technologies, especially if you're in an established organization that's got sort of your way of doing things. You're going to be hitting that pretty hard. There's this sort of middle ground. We call it the point of the spear syndrome. And what we mean here is that you're sort of doing something first, which means you've got the toughest thrust forward of anything. But because you're a spear, you actually have pretty good life behind you. So what is a pain up front, and we'll show you what that looks like, also carries some pretty good benefits for being first. We couldn't quite put that in either category, so it sort of sits in the middle here. And there's some definitely some wins, and this is, for us anyway, why we think it does work. We'll talk about these. But basically it boils down to this. You get really revolutionary technology solutions, and I'm not using that in sort of the buzzword sense. I mean flat out revolutionary. Right? Things will change. You will be able to do things you couldn't imagine having done before, much less actually tried. Right? That's what revolutionary is all about, and you actually do get that kind of a solution. You get to reset your scaling base, meaning all of your math that you've used to figure out how long your business is good for in whatever domain, especially from a technology perspective, all of that stuff gets reset. You don't get that very often, but you get it here. And it allows you to not only do new things, but you can take on entirely new problem sets you never thought about before, which is an enabler for your business, especially if you're trying to grow. Like one of the things, everybody's aware we're splitting the companies right now. In fact, that's mostly what we've been doing for the last 6 months. We are excited because we hope to be able to, as PayPal on our own, take on completely new things from a business level that we haven't done before. And of course, you get to leverage new resources across the organization. I'm going to leave that as it is for right now because I think I'm going to surprise you with what I call a resource as we go later on. So, some technical challenges. Simply put, HPC technology is not simple. However, it is also not needlessly complex. These are computers. They still boot. They still have all of the same resource dimensions that you're used to. They cannot be managed in the same way that you're probably traditionally used to, and that adds complexity, mostly because of change. They are not some completely an alien race that breathes differently, right? They are computers. They function the same way. So it is complex, but it's not different. This next one is probably the hardest one. Your independent functions as resources are dispersed. And what we mean there is, especially in the enterprise world, we're very used to contacting the IT guy when your laptop has a problem, and contacting the storage guy when you're out of space, and calling the network people when something can't talk to something else, and the firewall people and so on. That doesn't work very well with HPC technology, right? The system is tuned for performance, which means that all of those work in concert, and one change on any one of those dimensions can have dramatic impact on the rest of the system. And so if you're used to running your organization in that fashion, you have to stop. Period. You have to develop people who talk. And they have to get used to working one. This is another one, this fragility concept. Fragility is a perception, and by that I mean they are computers. They do stay up on their own. It's not like they went out to the store and said, find me the components that fail the most but are the fastest. No one's ever said that. Right? They don't really say things like that, right? However, because they are used in a different way, and because the system is tuned like that ecosystem that we've been talking about in such a way that the one drop of oil does make a difference, then you can perceive fragility if you're used to kicking your system around. And in my world, we were used to some extent, kicking our system around. So it can be a real perception, but it's real based on how you tend to use the system, not on the notion that the nodes themselves are sort of prone to failure. They're not. On a vendor side, the HPC vendors are just now starting to understand enterprise needs. I think that's why we're all here. Which means that you will spend a lot of time trying to explain things that you think are common sense. The good news is they want to help and they are listening. So do yourself a favor and push through that particular part of the headache and explain what it is that you're trying to do and why you're trying to do it. They will listen and they will help you. And the cool thing about HPC vendors is they, for some reason, get very, very invested in success of your system, much more so than I think the enterprise vendors do. Enterprise vendors, they are interested in your success, but not to the degree the HPC guys are. So I think that's a resource you can leverage going forward. So a little bit about the notion of Formula One cars and sporty sedans. The HPC guys, we'll call them the Formula One guys, they design first and foremost for performance first. I learned more about the specific notions of differences between chips in the first month that I started doing this than I probably ever cared to know. In retrospect, it was a good thing. I needed to learn it. But if I've carried one thing from that sort of learning curve I had to jump up effort, it was an awful lot of work that didn't really have any direct bearing on what I was trying to do. But it helped me talk in the same language with the HPC guys about what they cared about, so I knew how to make my differences understood to them. So yes, performance first. They're all about how fast things can go. And so sometimes it's okay to fix your system Monday through Thursday so you can drive it really fast on the weekend. Towards that end, their reliability model inside of HPC tends to be focused on what I call checkpointing here. It tends to be this notion of batch or codes that run, and their attempt at resiliency is based on try again. So we build in this idea of marking off how far you've gotten along the path of whatever it is that you're doing, and when things go wrong, and they inevitably do, then we just try and go back to the most recent thing that we did and we start over. That is, from an enterprise perspective, an extremely rudimentary way of looking at resiliency. So that may have sounded and come across mean, but I meant it to. Right? This is not the way you should be doing resiliency. This is 1980s thinking for how to handle some of this stuff. On the flip side, enterprise guys build sporty sedans. Right? We care about reliability and scalability. They battle back and forth for first. And when we say scalability, we mean scaling the function that something's trying to accomplish, not the system itself. We couldn't care less whether or not the system is up and down. We have this notion, we have this idea, we leave the injured on the field for the most part. When things die in our racks, for us, most of our small soldiers, we don't repair them. We just wait until a rack is more than 60% failed out, and then we swap the whole thing out at once. We don't bother to pick the injured up off the field most of the time. Which is, again, that's a little bit different from the mentality of trying to get every ounce of performance out of the system. You want all those guys up and running. We do tend to use small soldiers, and we are very good at it. It does not scare us in the least to say that we're going to run 100,000 computers in this data center. That doesn't bother us. We're okay with that. In fact, our scaling unit buys 250 computers at a time. That's our smallest increment of stuff on the enterprise side that we acquire, is 250 nodes at once. So, sometimes people come and go, isn't it hard to manage all that stuff? No, we got it down. In fact, we can teach the HPC guys a bit about how to run clusters, right? Because we were good at that. And we have this idea of as long as it's up. And again, the it we always talk about in the enterprise space is whatever function we're trying to deliver to the business. It has nothing to do with whether the system is up or not. The system we don't really care about. What we're after is, if my job is to process a payment right now, I need to be able to process that payment. I don't care which component actually carries out that payment, as long as when you think it's time for you to hit a button and do it, you can make it go through, it's okay with us. We call it alive enough. It's okay, right? As long as you're up, degraded is okay. Probably in the end, then what we're looking for are indie dump trucks. I love this picture. Right? This is probably the blended idea, and it's probably not what anybody wanted to be out there racing. However, this is the reality of what this enterprise and industry stuff means, right? We're going to leverage HPC resources to add performance to the overall system. That means things like process locality matter, right? We want to pay attention and learn how to do that. That's something that's new for us. We want to obey and look at data laws of motion. What I mean there is that data behaves and should be accessed and controlled differently based on where it is. Data at rest or in situ has one set of attributes and behavior characteristics and should be optimized accordingly. Data in flight has another. Data that's being split and moved to different places has yet another. So where your data is in flight and at rest, we want to learn to optimize those, and the HPC guys are very good at things like bringing compute to the data at rest and stuff like that. Interconnect is the easiest one, and it was our first steal. So we actually acquired InfiniBand as an HPC interconnect between our nodes before we bought anything else. strictly because of the benefits that we got there. And I think that that is still one of the best things about HPC is not only that the interconnects are actually faster and lower latent, but that they've recognized that the interconnect itself, as we grow forward, becomes a place where you can do consistent data operations. In other words, you can use it to extend the boundaries of what you call a computer. And you can do that in a way that doesn't penalize you in the sort of traditional out-of-platform sense. That's something that enterprise needs to pay attention for. And of course, direct memory access is an extension of how you treat the interconnect there. On the flip side, what do I think that we retain? I think we go from small soldiers to bigger ones. And so, when you sit down and you're working out buying your first HPC cluster for use in the enterprise space, you will probably need 2 of them. Well, you definitely need 2 of them, right? Because there is no cluster out there that has figured out how to isolate failure enough so that you can trust that the cluster will always be up. So you will always need 2, and you'll have to spread your workload across the 2. To be honest, you'll probably need 3. Because there are some situations where one failure type will immediately assault the other, even in a split 2. So in our world, we spec'd out, SGI was the first person we bought a cluster from. We spec'd out a big one, and we said, great, this is what we want. How do I split it into 3 parts? Which they were like, what? Why would you want to do that? And I'm like, because you haven't told me how this one going down is going to keep all the rest from going down. We're like, well, it doesn't. They're like, right, so how do I buy 3? I want the same number of machines, but I want it split into 3 parts that are independent. So you will probably need that. The good news is, smaller is okay. We're okay with leaving some performance on the table. That's all right, right? It's still going to be infinitely faster than what we had before. We have to learn not to leave the injured on the field for too long. That doesn't mean that we don't leave them on there. For example, right now, I have a big shared memory system. It has 32 cores and 2 terabytes of memory offline right now. Has been for 2.5 weeks. I'm going to leave it that way for another month or so before I get it worked on. Why? Because the work that I'm doing on it is more important in functions in the remaining part of the system than it is for me to take it down right now to have that board replaced. Again, it's a weird, it's a different mentality, right? I care more about the work going on than I care about the system being worked on. It's okay for me to leave it dead for a little bit. Leverage the services where possible. And what I mean by services is no more batches, no more codes, right? You have a job that does something, run it. We're used to things like web servers and name servers and DNS servers, and we had a whole talk yesterday on SaaS, right? All that kind of stuff works great. The good news is it works great on top of the HPC systems too. They're just running Linux, people. It works. You will raise some eyebrows with your vendors, but just keep nodding at them and going, it's Linux, right? It'll work, it'll work, it'll work. And the good news is not only does it work, it usually works a little bit better than what you expect. So some of the social stuff.
All right, so sometimes we forget that there's a lot of social aspects internal and sometimes external to the challenges that we've had. There's a lot of misunderstanding. When we talk to our management and we talk about HPC, originally they're like, HPC, what does that mean? They just don't understand. So a lot of the things that Ryan and I have been doing inside the company is evangelizing HPC and making them understand what HPC is and showing them the benefits that they're deriving. And that they're allowing us to, they're giving us budget to actually expand and move forward with a lot of things that we're thinking about. Something Mike said last night, people are resistant to change. They're very comfortable where they are in their jobs, in their careers, and they're resistant to change. The things that we're talking about is a huge change. It's a sea change for us, for PayPal, but it's also a sea change for a lot of enterprises that are looking at HPC. People need to either, not as drastic as what Mike's company did, but they need to step up and move forward. If they can't move forward, they have to maybe go back to traditional enterprise environments. There's also a method of people have a hard time of applying new technology to problems, existing problems. And something that Brian and I have been able to do, part of our jobs in the Advanced Technology Group, is to look at technology 3 to 5 years out and understand how that's working and how we can apply that new technology to existing problems we have today and maybe leapfrog forward a little bit. And that's kind of where we've been heading in the last 4 or 5 years with HPC. And in terms of analytics, that's a huge problem there. The people that are required to do, and the data scientists that are required to do all the analytics, there's a huge gap there. And I think the latest numbers I heard at a conference a few months ago was there's a shortage of about 300,000 data scientists in the world. So if you want to change careers and become a data scientist, you'd probably also double your income. But it's something that we have to be very worried about, because all this big data that we're hearing about over the last few years, there's not any data scientists to actually start analyzing it. So between the shortage of oil and gas people and the shortage of data scientists, we're probably looking at some real world problems in the next little while. We mentioned point of spear syndrome. Now, we are unfortunately at the very point of the spear. We're leading a charge into a new technology that most people aren't familiar with inside our enterprise. So a lot of organizational structures are changing. People are concerned about their jobs. They have to make changes to the way they work. We have to make changes in the way we account for buying servers. They're not used to, like Ryan said, we buy 250 servers at a time. When we buy an HPC system, they're not used to one single SKU, for instance. They don't know how to build that. They don't know how to put it to the right cost center. So there's organizational changes inside the company that need to start changing. We also have a different way of accounting for the systems in terms of how long do the systems last, capital depreciation, et cetera. So these are things that normally enterprises don't think about, and we're bringing them forward as one of the social challenges that we've encountered over the last couple of years, bringing these systems in place. The other thing is about ownership of the systems. Once we're very successful with the system, people want to say, okay, we want to own that system because we think it's important for our group to have it. Well, these are internal problems that we've faced, and we're working through those. So just for those that are looking at blending HPC and enterprise, just be wary of some of these social challenges that you'll see internal to the environment.
The good news, though, again, with point of spear, is that the rewards for it are large and they live a long time. It's also neat that you get an early success, because the whole reason you're buying this in the first place is to solve a particular problem. So the good news is it'll do that. Great. So you get it out there, you get an early success, you have a very short time to market for that particular initial push of the spear, and it'll work. And it's cool. This is another thing that's great to leverage about how people work. When you're trying to get it done and you're trying to convince the asset management guys that buying a shared resource and then accounting for it on the books is something we actually can do, believe it or not. Once you win that war and you get it out there, then everybody is like, hey, this thing is neat. You guys bought a supercomputer. We want to help, right? So use that to your advantage, right? Once it's out there and you've got those early successes and everybody wants to jump on board, resist that urge to be like, where were you when, 6 months ago when I was trying to get that? Put your arm around them and be like, great, now let's figure out how to do the next stuff. And you'll be surprised at how cooperative people will suddenly get. Use it to your advantage, don't hold that grudge. You want you'll be able to develop an internal business strength there for handling multiple computing paradigms. And so that means if you think of it in terms of Batman's belt, you've got another tool out there that you know how to use, right? So where you were able to tackle challenges around building a service or deploying a database automatically or provisioning a lot of small systems or being able to put web servers internationally. Now you've built a muscle on how to aggregate disparate data sets together or be able to perform data analytics at scale on things coming from different places. These are new tools that you can use to approach different problems with. So make sure you call those out and let people understand that you've not just given yourself more technical capability, but you've given yourself more business capability as well. And of course, along that you get a unique opportunity in the beginning. You'll see we are actually still writing this last bullet. You get a public relations uplift, right? Because of that cool factor, right? And you're doing something that's never been done before. So when you're successful with it, talk about it. Let people know. It'll help. You'll get a talent uplift, right? You'll suddenly be able to hire folks that wouldn't have looked at you before because they didn't think you were doing the types of work that they were interested in doing. This is great. You get opportunities to collaborate and work with industries and groups from all over. A lot of you guys are out here that have worked with us before over the years on various and sundry different things, or are working with us now. To us, this is very refreshing and neat. We get to repeat this cycle over and over again. That's lucky for our team because that's kind of what we do, but it's also big for the organization as well. So look for opportunities to be able to do those things in a way that help long term. You get to, good news, resetting that scaling baseline. Again, all those things there, the compute, memory, storage, you get a lot more tiers in the storage than you probably had before, including different types of memory and things like that. Again, all that stuff is storage. Your interconnect starts to bring in some of the stuff from above it. The compute, memory, and storage starts to be brought into the interconnect, and therefore it can start to extend on different dimensions. Virtualization is actually one that I put on this list. You don't see that much on the HPC side of the house, but it's very big on the enterprise side. The good news is virtualization works great on HPC gear, right? In fact, it works really, really well. And some of the extensions from folks like Mellanox and things like that in the last 6 months or so have actually pushed those capabilities into the virtual machines farther. For us, and you heard it last night, they were talking about doing Docker and containers and that kind of thing. Those types of optimizations make it very easy for us to be able to put new applications out there and things like that. Again, we're willing to leave a little bit of performance on the table. But one thing that you guys probably don't realize is that the performance differences are almost negligible now for virtualization. So I just did a talk last week where I did some numbers, and we were moving databases around. We could tell no difference whatsoever in database performance, again, running on top of scale-out cluster between running it on bare metal, raw I/O throughput, and running it inside virtual machine. There was literally no difference between the tests. So if you're still under the impression that virtualization is going to hurt you by 3 or 4, 5, 10% or whatever, that is flat out not true anymore. So go back and look at it, because it's not like that anymore. But again, the coolest thing is here is you break your lockstep. So if you're used to scaling by those units of 250 at a time that give you a certain amount of compute, certain amount of density, a certain amount of storage, a certain amount of memory, you get to break that. Right now you've got a way that you can scale things at different rates. And if that works and it becomes cost effective, then by all means go for it. You get better solutions for the problem that you were after, but you also get a new approach to solving the problem in the first place. And many times that's what has the longer legs in the organization. It's not just getting the early win, but getting a new mechanism by which you can solve other problems is worth it, right? It's one thing to be able to figure out that 1,000-piece puzzle. If you remember the first time you took on a puzzle that was like beyond what your scope as a kid, and you figured it out and you were like all proud. But what was cool is now you were in a whole different class of puzzles altogether. Once you did that first one, right? Then all those other ones on the shelf that looked much cooler than the smaller ones, that was what you were able to, that became your new ground for acquiring puzzles from. It's the same thing here, right? Once you break through, your class of puzzle increases, which only helps your business. So you get new capabilities, you get to take on wholly new problems that you never considered before, and you get to add new business skills and resources in complex dimensions. This is what we mean not only by crossing over silos. So, like I said, your network guys are going to have to talk to your storage guys, and they're going to have to talk to compute guys now. They all have to work together on these types of things. However, when you do that, you get a new Lego, right? And that, to a business having, it's not just being able to build a house out of the components that you've got, but getting a whole new shape of Lego is something that's really cool, right? And so, you get some of these. Is this one yours?
It's yours.
Okay, sorry. We lost our notes earlier today, so we're trying to remember. So what do I mean? Some new business level resources. Data marshaling is a skill. It's not just something that you have to do. It's something that you can excel at and that you can build real business understanding around. How to move data around in this big data world that we're in is really, 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 really important. And we don't talk about it nearly enough. We talk about how cool big data is, what people are doing with the data, how they go about ingesting it and understanding all that stuff. But I'm telling you, moving it around and understanding the ways to optimize that and what you can do with the data at different places as you move it, that is what's going to differentiate folks with big data, right? Because knowing what to pick and when to pick it is how you win the who got there first game, right? Everybody can operate on a data set that's at rest, and you will be able to get all kinds of insights out of it, right? But finding out something that would have been relevant yesterday is only of interest to historians, right? Finding out that something that would have been relevant yesterday, that changes your cost and savings model, right? So this data marshaling skill that you can develop is really, really important. Data analytics, as Arno mentioned, this is one we've actually got a dearth here. We got a lot of people that know data science out there. We got a lot of subject matter experts. But as Tom Davenport says, to paraphrase him a little bit, leaving the data analytics to the data scientists data itself is too important to leave it to those guys, right? You can't leave the data in the hands of the subject matter experts because they're subject matter experts. They know about content, not data. They're different, right? But you get to build a real skill set in-house inside the company around understanding what data is like, what kind of characteristics does the concept of data have, and how can they be mined, how can they be understood, how can they be disseminated throughout your organization, right? That's a real skill. And it's independent of the guys who are actually understanding the content of what the data is about. It takes a lot you have to do this for a while before you start to get those subtleties there, but trust me, they actually are there and they're important. Workload placement is another thing that you'll get real skill at, right? You'll understand what types of loads work better in different types of systems designs, and you'll be able to optimize and move things around. The fact that you have different places to put workload now is great. The fact that you get really skilled at knowing where to put each one and then being able to automate putting it there and treating it, that's another skill that you get. Parallel programming, we said it again. It sounds very old, I think, to most of the HPC guys. We're like, well, of course you're working in parallel programming. I've been doing this job for 20 years with Java. Java is multi-threaded, but it's not parallel programming in the sense that we're used to. So for us, being able to actually eke some of that extra performance out of the system without having to sacrifice our ability to use high-level and functional programming languages, which we are not about to give up because they are far more profitable to us, is great. So it was, we talked with James Reinders last week. He's sort of one of the big gurus in the parallel programming space, and even he is starting to slowly budge and realize that, if it takes me 6 months to optimize a piece of code before I can run it, or I can have a piece of code developed in a couple of days that is 80% optimized, guess which one I'm going to pick in the business every single time, right? But it's in his best interest to help the compilers get to where the automatic 80% is given to us all the time. And I think that's coming, and you'll be able to develop some internal business skills around recognizing when you need to make those calls and when you need to optimize there. So back to our original question. Oh, I cut that bottom of that slide off. So that quote there is from Through the Looking Glass, and the whole thing is, "The time has come, the walrus said, to talk of many things, of sealing wax and sailing ships, of cabbages and kings, of why the sea is boiling hot and whether cabbages have wings," right? The point there being, the walrus talks about all kinds of crazy stuff together, right? That doesn't seem to make a whole lot of sense in the context in which it was given. But deriving the understanding about that gives us the book Through the Looking Glass, which is widely recognized to be a classic. If you just went around quoting that to people, they'd be like, what on earth are you talking about? But in the wider context of what the book is about, we start to get real insight. This is the kind of thing that we're talking about with blending HPC together here. So, is it worth it? We think so. We think it's definitely worth it. But for a couple of reasons that honestly we haven't mentioned yet, but we think are important. And the first one is that the enterprise can't just do big data. They've got to do better things because of big data, right? Right now, big data is a buzzword, and it's sort of this end to itself, and in all of its forms: big learning, big data, big marshaling, big whatever. Big data is just a measurement in some way of the amount of work you're trying to do. What you do because of it, that's what matters, right? And that's one thing that we think is crucial. They're not going to get beyond handling the big data to doing the better stuff without blending some of these technologies together. On the flip side, exascale, sorry, is not an end. I couldn't care less if we ever built an exascale machine if our only goal in life was to build a very big machine. The reason that exascale matters is because we have ends to achieve that we cannot achieve unless we have systems capable of achieving them, right? Exascale thinking, exascale problems, those are the kinds of things that we should be focusing on. The news, though, is you're not going to get there unless you can handle and understand data in some of the ways that the enterprise guys have figured it out, right? You've got to learn to message, right? Moving giant data sets around just for the sake of moving them isn't going to get you there. Figure out what you needed to know out of those data sets, keep that around persistently, and then bring that in. Use them like that augmented stream technology and add them to there. And your overall capability increases, but the amount of actual work you're doing goes down. No one says we can't solve exascale problems by doing less work. But it's weird. I haven't heard anyone propose that. But that's my way of coming about it. How can I solve this exascale class problem by doing a petascale worth of work, right? And that's one of the things that the enterprise guys are very good at doing. We can look and learn how to cut down a workload. We learn and we grow and we expand in our own lives through creating and using better building blocks. Think about a problem that you take on as yourself. You don't think about the roles that your eye has in solving the problem, or your hands, right? Or your mouth in speaking a solution. You don't think that way. You think about what you as a person can do, and when it's bigger than you think what can you do with multiple people, right? Especially as we're all managers, right? What can we do with our people that's bigger than what any single one of us can accomplish? This is the type of thing that I think these blending give us. Get better, cooler, bigger people, right? That we can use as a community to bring to bear on these types of problems. I hope that makes sense. So, do I think blending in enterprise and HPC together is a good idea? I absolutely do. But the reason that I think it's very important is because we need different ways of solving problems. And we need different ways of acquiring problems on both sides of the fence. And we're not going to get there unless we talk a lot more than we have been up till now. So, that's it.
Thank you.
We have time for 2 questions. 2 questions. Yep.
There's one.
1 second. I'll be right there.
Are you working with the Berkeley AMP lab at all? And what's your thoughts about the Spring technology and Pivotal and the Spring XD technology for data ingestion?
We have not worked directly, meaning person to person, with the AMP lab yet. We have borrowed some of their technology. In fact, last week I presented some stuff about Spark running on UV, actually. It's not for lack of want, it's just a lack of time. You're looking at the entirety of our team here, and so we have a laundry list of stuff we want to get to, but haven't gotten there yet.
Hey guys, thanks for really fun, cool talk. It's really interesting to see these other things. So I just had a couple of quick questions for you that are maybe a little more technical. One of the thing is, what do you guys use to enable your self-healing environment to process the feedback from the analytics?
So we have different tiers of command and control from a monitoring, alerting, and a response. We tend to use Nagios for bringing all of that stuff together, but we don't necessarily use Nagios itself to bring about the self-healing, though we have. So sometimes for very simple cases, like some lock file is still stuck out there and all it needs to be is removed, we might use the Nagios methods of going out there and getting it. We use a lot of CF Engine, not for distribution purposes, but for enforcement, for that kind of stuff. And then inside the application, we'll actually write methods to go and help fix it. So we may collect an event in Nagios that says, hey, this database looks to be marked down, but marking up a database, so our application, for example, has hundreds of databases that one application will talk to all the time. At any given time, one of those databases might be offline. It could be as simple as we're moving it from one place to another. It could have been a network blip between there. There's tons of reasons. But from the perspective of the app, one of the databases is down. that doesn't necessarily mean the database itself is offline or something. So that type of logic, we actually have a more sophisticated check for. It goes out there and says, can I talk to the database? If the answer is yes, then I'll go out there and tell the application, just mark it back up, it's okay. If it goes out there and it can't, then it'll say, will somebody in the local data center to that data, can it talk? And it does a bunch of different, so it sort of depends, but we generally use Nagios right now to sort of, I don't know, herd those cats.
There's also various levels of remediation that we're allowed to do. For instance, we can't flip the site completely based upon what we're getting from our system, because that's just too much.
Not yet.
Not yet, but we do want to get to that point where our system is so ingrained and so understanding of what's really going on that it makes sense for our system's intelligence to make the change more so than humans, because we understand what's going on across the whole system. But the idea is to flip the site to another data center if we have to.
Or components that could function in another place, we can move them all at once, kind of thing.
Cool. The last quick question is, what's your virtualization system that's so non-different from bare metal?
We have, again, various and sundry ones. Pretty much everything you've heard of, we have out in the data center somewhere. Though on our system, with the HPC gear, we tend to use KVM or Zen.
Gentlemen, thank you very much. I'm sorry to cut it short, but
All right.
time to